Okay, I also have this MRI simulation. Okay, this might need more work. We have 5-minute notebook LM overview on this one.
So the core idea of this simulator, its real strength, is showing you what's normally invisible. It shows how all those hydrogen protons in your body, which are everywhere, especially in water, how they react when you put them in different magnetic fields.
Right, and it's that reaction that produces the signal MRI machines detect, and it turns physics into something you can, like, click through.
Well, let's walk through it. The first step you see is apply main field, B0.
Yeah, and this is fundamental. When you click that, you're seeing the effect of the MRI's main huge magnet. It forces, well, encourages, the majority of those hydrogen protons to align themselves with that powerful field. It's fascinating, really, how your body's own atoms become the tools.
It sets the stage, basically.
Precisely. Without that initial alignment, that baseline, you can't really do much else.
Yeah, okay, so things are lined up. The simulator then prompts you to apply RF pulse. What's happening there?
Oh, this is where we add a little energy into the system.
Think a nudge.
Exactly like a nudge. It's a very specific radio frequency pulse. Think of it like flicking a spinning top just right.
Okay.
It tips some of those line protons out of alignment with the main field. They absorb that RF energy. And that tipping is absolutely crucial because they won't stay tipped forever.
Right, they'll want to go back.
They will. But before they do, we need to know where they are, which
But-
brings us to the next step.
Apply gradient. This always felt like the bit that makes the picture possible.
It absolutely is. This answers the big question. If you get a signal back, how do you know if it came from, say, your knee or your ankle?
Right, location, location, location.
Exactly. Gradients are these weaker magnetic fields that we turn on and off very quickly, and they slightly change the main magnetic field strength across the body.
So the field isn't uniform anymore.
Correct. It varies predictably. This makes protons in different locations wobble or precess at slightly different frequencies.
Ah, like giving each spot its own little signature frequency.
You got it. That frequency difference tells us where the signal originated along that gradient. That's spatial encoding.
Yeah, very clever. And that leads us to the final click. Detect signal.
Yep. So the RF pulse is off, the gradients have done their work in coding location, and now those protons that got tipped, they start to relax back into alignment with the main B0 field.
And as they relax,
They release that energy they absorbed from the RF pulse. They emit their own faint radio frequency signal.
the echo, basically.
The echo is a good way to put it. And when you click Detect Signal, the simulator visualizes capturing that echo. That signal contains information about the tissue type and its location, thanks to the gradients.
It really simplifies it down. The click-by-click nature makes it so much clearer than just reading about it.
It does. It's very direct.
But while this covers the basics brilliantly, the source material also mentions what's next, where this kind of simulation could go. And here's where it gets really interesting.
Oh, definitely. Even this basic model hints at the sheer depth of MRI physics. The future directions they talk about are quite exciting.
Like what?
Well, things like simulating more complex gradient fields, showing not just frequency encoding, which we touched on, but also phase encoding, another way we pinpoint location in 2D or 3D.
Okay, so getting even more precise.
Exactly. And also showing signal decay more realistically, things called T1 and T2 relaxation.
I've heard of those. That's about how quickly the signal fades, right? And different tissues have different times.
Precisely. Crucial for telling tissues apart, distinguishing muscle, fat, water, and importantly, healthy versus diseased tissue. Imagine seeing that visualized. And they even mention basic image reconstruction, showing how you go from those detected signals, those echoes, to an actual recognizable image on the screen.
That would really connect the dots.
It really would. It shows how even a simple tool can be a gateway to understanding immense complexity.
So pulling it all together, what does this mean for you listening? You've basically just walked through the core physics of an MRI.
Mm-hmm.
You've seen how that main magnet aligns protons, how the RF pulse tips them, how gradients give them a location stamp, and how we detect the returning signal. You get the fundamentals now.
And it shows the power of these interactive tools, right? They demystify things that seem, impossibly complex. Makes learning active, not passive.
Totally agree. Which brings us to a final thought. Think about all the other complex tech in our lives. What if you could simulate those?
Oh, interesting.
What everyday machine, maybe your phone's processor, or even just how your microwave works, would you want to see unpacked with a similar interactive deep dive next? Something to ponder.
Yeah, don't think we'll be simulating a microphone, a microwave or a microphone. Well, actually, a microphone is closer to biomedical stuff. A microwave, yeah, could be interesting, but I'm sure someone did it before. Yeah, let me know if you can find the microwave simulation or an MRI simulation. Maybe someone, I'm sure there are some simulators, but the question is, are they readily available and work in the browser? So there's some weird things about it it does make sense. Applying main field, applying RF pulse, applying gradient, detecting signal. Does it make sense? Does it make sense?
Everything we do is available freely on bionicchaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.